Now, the next topic is red versus green light. And you may notice that if you're wearing a smartwatch, that on the back of your watch, the green light is usually on, but occasionally the red light turns on. And the real reason that red light turns on is to measure oxygen saturation, not just heart rate. And the reason red light or infrared light is used can be identified in this absorption versus wavelength plot. And you can see here in the red region that you have basically the deoxygenated and the oxygenated form of the hemoglobin. And you can see that the absorption of these two are very different within the red band, whereas in the green band, the differentiation is not that clear. And for that reason, therefore, oftentimes these devices uses two forms of light, the red and infrared, both sort of on the opposite side of what's called the isospastic point. This is the point where the wavelength of light is absorbed about the similar level of both the deoxygenated and the oxygenated hemoglobin. And so because there's such a contrast here, you could use the data that you get in terms of the amount of light that's being absorbed for the red and infrared to subsequently calculate the oxygen saturation that exists in the tissue. So this is the reason why you have red light visible on certain occasions, because it's actually monitoring the oxygen saturation. And you may not actually see infrared because infrared's not in the visible region. So the question is, why green? Like, why green at all? And so green presents the optimal balance between good hemoglobin absorption and just the right amount of scatter. And so you can see here that there's a high amount of hemoglobin absorption of green light compared to the red. And the other thing is that scatter of the green light is low enough to go to the capillaries of the upper dermis, but high enough to allow a shorter path length between the source and the detector. And remember the Beer-Lambert law showing the exponential attenuation of light. A shorter path length would allow less need for a higher light intensity. And this leads to less consumption of LED light or power, and is also less prone to motion artifact, because the more you move, the more likely that you're going to have the underlying tissue move, and as a result, sort of affecting the results. And this might explain why that when you have the pulse oximeter light on, or the red light on, it requires a higher intensity and therefore drains the battery much more than the green light. And you could kind of see this with a nice demonstration of the differences between the visualization that you get with these different lights. And this is based on the pinnae, or the routed ear, where a vascular tumor is implanted and grows in size. And so the red light is actually pretty good in terms of penetrating through the ear, so it requires a lower intensity. But because the green and blue light absorb hemoglobin so well, which you can see here compared to the red light, you can really see the details of the vasculature in the ears and also the tumor. So the tumor is just much more highly demarcated, and you can see that none of the green light leaks through this tumor, whereas some of the red light leaks through that tumor, which is highly vascular. And to sort of demonstrate the differences in its sensitivity of motion based on these different lights, this was a nice study done by Matsumura in 2020. And this study evaluated the effect of motion on different types of PPG signals, both reflectance and transmittance, and the different light colors, which include blue, green, red, and infrared. And they also assessed it with, again, reflectance. So basically, you could see here that you have these 4 photodiodes of different colors, and then you have the sensors of the photodiode sensor on the same side. So this allows for the reflectance PPG. And you noticed here that the green and blue are closer to the sensor because of the scattering. And again, that was that path length that I showed in the previous slide. And then you have the photodiode on the opposite side to allow for transmittance of the light, which will be red and infrared, to go to the opposite side. And what this study did was they recruited 12 university students, and they acquired PPG data along with EKG and accelerometer data. And they measured PPG at rest, and also while they were doing a rapid sort of shaking, both horizontally, just like this, and also vertically like that. And what they did was they took the Fourier transform of the PPG signal, of the EKG signal, and also from the accelerometer, and just tried to assess sort of the signal noise ratio. And you could see here sort of the results that you get during baseline. So baseline means that there's absolutely no motion. And so you could see the accelerometer showing no acceleration here. The EKG shows a nice sort of RR interval, the delineation of the R waves. And then you could see here, this is RB, which is the reflectance of the blue, reflectance the green, reflectance the red, reflectance of the infrared, transmittance, and then the transmittance of IR. And you can see that green and blue, at least when it comes to reflectance mode, has the highest signal compared to the red and infrared in both the reflectance and infrared transmittance mode. And then the other thing is that when you, during the motion, particularly in this case, I believe it's a vertical motion here, you could see that the signal that you get in the red and infrared, no matter whether it's the reflectance or transmit, is markedly diminished, or it has a lot of noise. Whereas in the green and blue signal, you could still demarcate the exact beat. And this has been sort of calculated out and sort of demonstrated sort of the mean values of signal to noise across the different conditions, across reflectance versus transmission, and also the color lights being blue, green, red, and infrared. And you could see here that overall, that the type of signals, the signal to noise ratio is higher in the reflectance mode for both the blue and green, and diminished for the red and infrared. And you can see that even for the horizontal movements, so this is baseline horizontal and vertical movements, that certainly the reflectance of the green and blue does the best in terms of obtaining better signals. And so I wanted to sort of give you a quick summary of the differences between red and infrared versus green light. Again, red and infrared light reaches deeper tissue levels compared to the green. Red and infrared is less affected by epidermal melanin. If you recall sort of the absorption versus the wavelength plot that I showed previously. Green light, on the other hand, is more affected by epidermal melanin. And red and infrared light is more suitable for SpO2 measurements due to the differences in the absorption between the oxygenation, deoxygenated form of hemoglobin. And as shown in the previous study, it's more susceptible to motion artifact compared to the green light. And I wanted to also incidentally sort of mention a personal experience that I had early in my career. I kind of dabbled in something called video PPG to extract heart rate. And as you know, if you take a video of a person, if the person stays still, the video can be analyzed. And so the video images each sort of is composed of pixels. So there are many pixels. And with each pixel, they each have an RGB component. So red, green, and blue components. And what I did at that time, I think this was almost 10 years ago, I kind of assessed the levels of red and green, blue components of each of the pixels and average it in certain zones. And to my surprise, I found that the signals that you got from the red light was really diminished compared to the green and the blue light. And that's simply because I just didn't know sort of the biophysics behind PPG until more recently. And so you can see that the green light does a better job of delineating sort of the heart rate signals. And the other thing that I also observed, that this video PPG approach really didn't work that well for darker skinned individuals. And as mentioned before, the melanin does absorb green light and blue light much more so. And so that explains why that individuals with darker skin just had poor video PPG quality.